your remarks and start again. Okay, so really this presentation is about the design and implementation of what's called a generalized algebraic theory. It's a particular mathematical construction that allows us to define, manipulate, algebraically combine quantities that are annotated with dimensional information, in fact, unit information. And the particular area that this focuses on is stock and flow models. I gave this talk in Washington, D.C. 2 days ago, on Wednesday, to a group of folks from category theory and applied category theory background. Where, some were more on the theoretical end, but many were fellow practitioners on the applied end. For this group, I'll change the emphasis and so on, but I'll seek to do it in a way that takes better advantage of the hour as well, and expands upon some points that I didn't so much emphasize there, and abbreviate some points which don't seem necessary. So the setting of this is going to be very familiar to I think everyone here, perhaps a bit less so Jeff, but it's the categorical stock and flow diagrams. All of you have at least seen it. And I'm going to talk about that just with a nod to it because we are here familiar with it. I'll then speak about the structure of dimensions and their associated units. And particularly the mathematical structure that applies there, which is then captured in Uji's a beautiful generalized algebraic theory. I'll then introduce this generalized algebraic theory for dimensional algebras, dimensional and unit algebras. But I'll do so with a bit of extra emphasis for this group on the general framework, giving some sense of what we're doing within a broader context. And then we'll look at how these dimensional quantities can be combined algebraically, both symbolically with some extra work being needed that Uji has led for normalization. And then in terms of concrete encodings as values where the dimensions too carry specific encodings in terms of Julia types. Julia being the ambient programming language around CATLAB and GATLAB by extension. And then we'll talk about some of where I'd like this to go. And, I suspect that there'll probably be multiple people here involved in that effort, and so we may spend a little bit more time on it. Okay, so everyone here is at a certain level familiar with our work, pioneered by Xiaoyan with stockflow.jl, and that work encompasses, as you're aware, multiple types of system dynamics diagrams and encoding them categorically for a variety of benefits. This includes transparency, modularity, extensibility, the ability to do things like combine them for stratification, combine them for composition, building things up out of smaller pieces into larger. It also includes semantic flexibility, which is something that Nastaran has really pursued to great effect, mapping these diagrams to different types of semantics. ODE semantics is ordinary differential equations, stochastic transition semantics, loop gain semantics, and eigenvalue elasticity related semantics, etc. But all of you will be familiar with the fact that, we have a schema, and by mapping this schema by having a functor into set, because C set, where this is the category C, we can encode specific stock flow diagrams. And using that construction, we can manipulate those stock flow diagrams in fruitful ways. So we can compose them. And in fact, we've defined something on the order of 4 or 5 different ways of composing them. This shows the most basic and most explicated, most heavily explicated, where we identify stocks that are held in common between 2 different diagrams. So we identify S here, for example, with S here. And by the fact that those are shared between these 2, we can take a push out, and rather than putting these 2 diagrams side by side, we identify as common that S stock, and we unify them around that, and they share that stock. Much as in a push out is like a coproduct, but where we identify certain elements as the same between the 2 things. Very much the spirit of what's going on here. And there's a deeper story involving undirected wiring diagrams and structured co-spans and push-out based composition and so on. There's a push-out square there, some may notice. But the intuitions that you might have from push-out applied to graphs or other C sets, carry over quite well here. We can also define homomorphisms between stock flow diagrams, where we, for example, find a stock flow diagram that in a way represents a pattern in another. So here, finding a first order delay in a different diagram. And by building on these tools, particularly homomorphism there, we can define larger ways of combining diagrams, for example, stratifying a given model by multiple domains of stratification and creating something here that looks product-like, but in general is going to be a pullback. It might be a connoisseur rather than taking the product of all combinations. It takes compatible combinations of these things, builds them up. But this facility allows us to define a stratified model in a more modular way. We get a quite descriptively complex model out, but we do so in a way that allows an economy of specification. And so this much more descriptively complex model can be characterized in a simpler way using stratification. Using these homomorphisms into a type model. Anyway, mostly just reminding you of this and giving the perspective. With that as the setting, with that context as being the relevant initiative that we're hoping to inform with this work, I want to now proceed to a basic understanding of dimensions and units as they apply more generally within science and within cognate areas such as engineering, etc. And I want to remind us that when we use the term dimension, we're describing a kind of reference, and I'm going to use that term differently from units, and this is important. I'm going to speak about dimensions and units, each with their own meaning. In fact, units are going to be specific to a particular dimension, like they're going to be fibered over dimensions. It's a bundle of units sitting over dimensions. think categorically about it. Each dimension has a set of different units. What's a dimension? Well, dimension describes the broad kind of quantity you're dealing with. Is it a length? Is it a time? Is it a weight? Is it a pressure? Is it, what sort of quantity are we dealing with here? It could be something that's like length per unit time, right? The speed of the airplane that I was on yesterday, right? Or it could be people per unit time, number of people getting infected per, or that associated with the flow. We might say it's a dimension, people per unit per time, right? And you'll notice that I'm not characterizing the measure there. I'm describing the kind of referent it is. And it is meaningless, and it's an important concept. It is absolutely meaningless to talk about, say, adding to quantities of different dimension, right? Like adding a person to a length doesn't make sense. Doing something like adding a length to an area doesn't make sense. One foot to plus a square meter. I mean, like it doesn't make sense, but plus a square foot also wouldn't make sense, right? A given quantity will have typically a very well-defined dimension associated, certainly for physical quantities. Now, by contrast, we think about dimensions, we can think as kind of fibered over them. We can think of each dimension as being associated with a set of different ways. It could be quantified, it could be measured. These are each associated, as it were, with different meter sticks or yardsticks by which we can measure, right? We could measure time in femtoseconds, seconds, hours, minutes, centuries, millennia, what have you, right? We can measure length in angstroms all the way up to light years, right? Parsecs. We can measure in inches or furlongs or what have you. Okay. Now, within this context of units, a given unit, as I say, it's fibered over dimensions, can be specific to a dimension. And a unit characterizes that standard of measurement, right? I said earlier, it doesn't make sense to add things of different dimensions. It also doesn't make sense to add things. It makes sense to add things of different units as long as we convert the units to be comparable, right? So semantically, it makes sense to say, okay, what's 3 days plus a week of time? It's just we have to do a unit conversion to convert them, right? They're the same dimension. They're both of dimension time. We just have to numerically, to add them up, we have to convert them accordingly, right? And a given quantity, let's say a length of time that I slept last night, right? That could be expressed in different units, right? I could elect to express it in seconds or minutes or hours or kind of weird days or centuries, right? If I were Rip Van Winkle, particularly. So a given quantity could be expressed in different units, but it doesn't make sense to talk about a given quantity being expressed in different dimensions. But I want to highlight that this fact again, that units are specific to a dimension. We're going to come back to that. Now, there's a structure to computing with and mathematically manipulating dimensional quantity, right? So when we talk about dimensional quantities, maybe we have, we want to quantify how, long is this phone or something, right? or the area associated with this little bag, right? If I want to specify the length of the phone, well, it's going to be associated with a certain dimension length. It would have no time component to it. To specify, I don't need to say anything about time. It doesn't depend on the unit of time. It's independent of time. It's a length thing, and it would be to the length to the one power. So it's one out here. It's length to the one. It's a length. By contrast, if I were specifying, and then the actual quantity, the specific value, if I chose to represent that dimension in terms of meters, this would have a specific value, right? Maybe it's 0.1 meter or whatever. By contrast, an area would be of dimension, dimension length squared. So it would be out here. This is the length dimension. Again, it'll be time to the 0 power, right? Length to the 2 power. So hence it's out here. And that quantity would then have a certain magnitude associated with it, right? Maybe this is, I don't know, something like 100 square centimeters or something. So it would be a value of 100. And so when we have a dimensional quantity, we can characterize it as carrying a certain value for the quantity itself, and then a product of powers of dimensions. So the exponents for so for each dimension, it has an exponent associated with it. So a length would be like squared. The L will be to the 2 power. Time would be to the 0 power. By contrast, if I had, the amount of time I slept last night, it would be time to the 1 power, length to 0 power, right? And we could imagine talking about the speed my plane was going yesterday. Well, that would be some length spatially, but per unit time. So it'll be negative in terms of the time axis. So it'll be down here. So it'll be like the speed of the plane, the velocity of the plane. And that would carry a certain value. So dimensional quantities carry a value, but they also carry for dimensions an exponent for each of our dimensions of interest, length, time, t to the -1, L to the 1, or for an area, L squared t to the 0. So we could write down that quantity, like encode it by writing out a vector of the exponents of each of the dimensions. 2 and 0, if we think of the first one as being length and the second one being time. And then the actual quantity would have a number associated, right? Why do we care about quantities? Why do we care about dimensions? Why do we care about them? Well, there's a lot of different reasons, and time is already rushing by, and I'm not going to dwell on these, but they're extremely useful. They prevent us from making mistakes in models. By de-dimensionalizing model, we can arrive at a model that has fewer parameters, and that means if we want to calibrate the model or we want to estimate the values for parameters for the model, we may be able to do so with fewer parameters. It can help us think through what the form that a formula could take, right? It can help us reason through scaling behavior of systems. It's how engineers build scale models of bridges or scale models of planes or of buildings. And there is remarkable science since the time where Joseph Fourier, the inventor of the Fourier transform, incidentally, and many other great contributions to mathematics and science, since he really first articulated the ideas of dimensional analysis, in the early 1800s, there have been remarkable advances in scientific insight supported by dimensional analysis. Okay. Now, so those are all, good reasons we might want to care when we are engaged in computation and we're reasoning mathematically about things, about dimensions and units. We want to avoid buggy models. We want to be able to reason about the scaling behavior. We want to be able to more easily calibrate them, whatever. But beyond that, for stock flow model, there's particular interests that are, I think, quite germane to my big motivation for pursuing this. And the reason that has motivated, UJ's working on this, a lot of these provided her, certainly me, direct impetus for this. In my view, dimensions and units are reflections of structure in the world. And in fact, there's a beautiful result called Buckingham's pi theorem, which is a very deep result, which observes that it must be possible to characterize. I mean, it takes this much further in a practical direction, but it must be possible to formulate any plausible theory of dynamics in a system out there in the world in a way that's dimensionally homogeneous. The world doesn't care about our unit system, and it turns out that these exponents and so on that we have in that dimensional vector of which I spoke, length per unit time, so 1 and -1, that the fact that, for example, the length of this was t to the 0 power meant that I can estimate the length of this phone or measure it without that value being contingent upon any unit system for time, right? If I quantify this, whether it's in inches or centimeters or furlongs or fathoms or light years or li or whatever, like that number will not change if you were to tell me that I'm going to change my units of time from days to centuries. Like it wouldn't change because it doesn't depend on, it's to the 0 power. And the observation is the world must be amenable to characterization. Like we have to be able to, whatever the governing equations are of systems around us. There's one thing we know. We may not know those equations, the formulas that guide them and so on. Those are evolving over time themselves. But there's one thing we know, which is when we change unit systems, with Canada switch to the metric system, the world did not crash, right? Like the world didn't care in terms of how planes flew and, how seismic tremors traveled and how winds blew. Like those processes in the world have to be amenable to a description. Whatever the formulas are, they have to be dimensionally homogeneous. They have to be describable in a way that is dimensionally consistent. And among other things, to state the obvious, whatever the formula is that governs, the Bernoulli principle behind lift on airplane wings, or that governs the spread of infection and, in northern, northern Saskatchewan of TB or what have you, it cannot be such that it depends on the unit system that's chosen. It has to be independent of that because the world is independent of our units. The processes in the world is independent of our units. And this provides huge insight. It's a reflection of structure. And this is one of the reasons, like, I think it's actually quite benighted to think you could just like explore all possible formulas and choose the one that best fits the data. Like that's ignoring dimensional structure. You need to take like the fact that we know this about the world, the fact that dimensional structure that the world must be amenable to description in dimensionally homogeneous fashion enormously greatly constrains the possible descriptions of it. When I say greatly, I mean it rules out a lot that are nonsensical. Just like a lot of statistical characterizations of the world, behavior in the world, can be ruled out because they're not dimensionally homogeneous. A lot of modeling representations can be ruled out. So whenever we try to deduce phenomena about the world, when we try to describe it with a model, we do well too. It behooves us, and in my view, it's kind of an imperative to do so in a way that's savvy to the units involved. And so we don't do something silly like adding time to dollars, or adding people to people per unit time or something like that, as two quantities of incommensurate units. So the fact that we know the world doesn't depend on our units actually tells us a huge amount about the structure of the formulas that govern things in the world. And again, this has informed a great deal of scientific insight. You look up the history of the Buckingham Pine theorem, and you find all sorts of fascinating things about it. Derivations, which are basically reasoning about the dimensional structure to arrive at some canonical formula. It must be this. The formula just has to be this dimension. Very powerful. And our group should take advantage of these things. So I'm very interested in capturing dimensional quantities. But why was stock flow? Well, look, this structural information gives us tremendous values there as well. How so? Well, look, if we're talking about homomorphisms, right, between models, like it only makes sense to find things here of a certain dimension with things of comparable dimension over here. We should take advantage of the dimensional structure when trying to do this pattern matching. Often we don't know, the particular names of these things, but we want to match like with like in terms of dimensions. Composition. If we go to compose one model with another, we only want to identify things that have common dimension, right? It doesn't make sense to say, okay, I'm going to identify something of person dimension here with something of count of birds over here. That's throwing away information that constrains our possible matching. So when we try to enumerate homomorphisms between models, and I would even wonder, like certainly between system structure diagrams, we can typically specify dimensions. And I would say even between certain causal loop diagrams, maybe we don't know what the unit is for measuring stress or measuring trust or what have you. But we might say it's a dimension trust. And that might constrain our homomorphisms between causal loop diagrams, for example, what we map to what. Similarly with stratification, if we're stratifying things, we talk about a type model. Some people will be less familiar with this than others here. Some people are intimately familiar. If we're constructing a type model, we probably want the type model to take into into account dimensions and only match up things that are sensible here to sensible things alike dimensions here. And you should start to get the flavor of this. Dimensional information can add constraints to our manipulations of these quantities categorically, like computing homomorphisms. And that may sound bad. It's like, oh, you're getting restrained, you're getting constricted, you're now you're being, limited what you can do. But it's not like that at all. It's actually, you can do things that are more intelligent. It can intelligently suggest homomorphisms and ignore ones that are nonsensical, right? Ignore ones that don't dimensionally make sense, that are not dimensionally homogeneous, would match people with birds or people with dollars or whatever. So what I'm saying is, like, some of you will recall, like when we find homomorphisms between stock and flow diagrams, or indeed between system structure and causal loop diagrams, right? We often will ask, what are the homomorphisms from A into B? And it will enumerate these homomorphisms, right? Well, now it can be more savvy about enumerating those and give us a smaller number of meaningful homomorphisms, ones that preserve dimensional structure, that honor the dimensional structure of the problem. And I hope that phrase reminds you of the fact that really, in my view, one of the, maybe it's the biggest thing in category theory. It's certainly a giant flavor, is right. Maps, not just as arbitrary willy-nilly maps, but as mappings that honor structure. That's what we look for, whether it's in talking about a functor from one category to another, or talking about a natural transformation, right? We're talking about pre-sheaves, C-sets. We're honoring structure. We turn composites in the source category into composites in the target category, right? Identities are mapped to identities, right? And when you think about, graph homomorphisms, we're honoring the structure of the graph, right? And here, this is a type of structure. Dimensional information has a type of structural equivalent. And by taking advantage of it, we can be a lot more intelligent in terms of zeroing in on the right homomorphisms we're interested in, zeroing in on the stratifications that we want, right? Being a lot more intelligent at suggesting formulas and stock and flow diagrams that are meaningful, right? Composing models in ways that are not silly, in ways that take into account the dimensional structure. This is powerful stuff. It's about being able to be a whole nother level more intelligent. And this is what I want. This is why I want to incorporate it within our stock flow to jail. Now, probably people here are less familiar than me. We also have explored with Nicholas Meadows hierarchical composition, where you take a stock with inflows and outflows and you replace it with a whole stock and flow diagram with compatible outflows and inflows. So you have an outflow out of the original stock and you replace it with a diagram of multiple stock and flow models of the same dimension. Get that? The stocks have to be the same dimension. And it has to have a flow of the same dimension out of it. It's kind of like you pop it in there and it just fits into the right, socket. Yeah. Anyway, there's upstream and downstream composition, which is kind of a variant of that. When you compose models, stick them together, and you have a jutting sort of outflow of the upstream model, and you stick it into the downstream model. Boom. But like that only makes sense if they're dimensionally consistent, right? It's a flow of people per unit of time. Flowing out of a thing of persons can only go into a thing of persons. I think you get the drift. And now those here are going to be less familiar with it, but I'm spending a lot of time talking with John Weiss and others about composition of machines. And soon enough in this forum, in our group, we'll be going through a really interesting paper by Sophie Lipkind and Kerry D'Angelo on composing stock flow models as machines. Okay, so let's go into the gap theory for this for dimensional algebra. Okay, so I think I'll go later on this, so I'll probably return to it. So this work is Uche's work, and I'm simply trying to present it to that audience in the conference. But the essential ideas here is that we define what's called a generalized algebraic theory. Uche defined one, which incorporates dimensional and unit. And at a technical level, if anyone watches this from category background, I'll note that it fits into this whole scheme. It's very closely related to this idea of graded quantities, so graded monoids in this case. And this is a notion in mathematics, which is one encounters every so often. It's quite big in certain areas, I think. And the idea is that we're going to have a generalized algebraic theory that will put that into place for dimensions and then some with units. And those who were present with for the discussion with Evan Patterson may remember that if we have a dim graded monoid within some ambient category, and the category of abelian groups, so each object is a group, but if this is a graded, dim graded monoids, then we're going to have M be a commutative monoid in the category of sets. So M, capital M, is going to be a monoid, and its elements are going to be n vectors of powers of length and time, and whatever else, people, birds, and so on. It's going to have the zero vector as its unit, and we're going to its monoidal operation, or combine them, is going to be plus, so we can add two n vectors together to get an n vector, right? And an M, so that's our monoid, or commutative monoid in the category of sets. Plus is commutative, right? So x plus y is the same as y plus x. Well, okay, so what's an M-graded monoid in a monoidal category V? Well, look, the category V is category of abelian group. So each object is an abelian group, okay? But we're going to have objects here for each in this abelian groups. We're going to have objects for each element of this. So there's going to be an abelian group where for things that are dimensionless, things that have unit dimension, 0, 0, 0, so they're exponents. There's going to be a abelian group, the same abelian group. Perhaps will be there for things of dimension time alone. 1, 0, 0. The dimensions are time, length, and people. So, There'll be an abelian group, the same abelian group. There'll be one there for, length or time to the -1, length to the 1 power. And person to the 0 power. So it'll be like velocity, right? There's going to be that same abelian group. So each abelian group is going to be there. And the important thing is that you may recall abelian groups have this group action, right? And this is group action. You can add things together, right? In the abelian group, right? You can add things together, and we can take the negation of something, right? So this is a group operation that can combine things and take the negation of it too, right? Take the negative. And so within times, we can sort of add them together, for example, with the abelian group, and we can take the negative of a time. Maybe strange, but if it's relative to some start time, that can make sense, right? And so we're going to have, the point is we're going to have an abelian group for each value of this, for each dimension. And then we can do things with that abelian group for that dimension. We can add things of that same dimension with the abelian group. But it's more than that. By virtue of being a dim-graded monoid, we could take the abelian group for, let's say, for time-related things, right? 1, 0, 0. And the abelian group for length related, let's say for people related things, 0, 0, 1, as a abelian group, and we can combine them by combining a quantity to get something with this tensor, to get something whose dimension is now the sum of the dimensions. So it'd be 1 for time, 0 is nothing for length, 1 for person. So we simply add the vectors up. This is the plus in our monoid. So we add those vectors, those dimensional vectors. And so now we have done something like multiplied the things within those given dimensions, dimension m and dimension n, and we have something whose dimension reflects the fact that we have quantities, the product of the powers, right? If this product of the powers for each is multiplied, and then the exponent sum, right? So if we have a quantity of time, and we have a quantity of unit length, and we multiply, and we get something of length time, right? Or person times, like person years, right? That would be a 1, 0, 1, like the example I was given. That might be for person years, for example. The number of person years that have played out in the simulation over the course of 100 calendar years, you've had 200 million person years, because some people died early, some people lived longer, and you integrate up the person years. So the point is, this provides us a way of getting within a given dimension. We have an abelian group. We can add quantities of that same dimension. We can subtract quantities of that dimension, right? Because we have minus. But then we can take quantities of different dimensions, and we can get a quantity of the product of those dimensions, which is the sum of the power, gives the sum of the powers. I think you get the idea. And then we have something of unit dimension, right? Unit dimension, that'll be 0, 0, 0. That's something that's dimensionless, or of unit dimension, right? And that's a morphism that we have in this dim-graded monoid category of abelian groups here. Okay, so anyway, that's the idea, but Uche has taken this much further. So she's defined a generalized algebraic theory to support this. And there's a lot of really sweet components of this that we can go through. Maybe what I will do here is, well, yeah, I think we'll just dive into it. I'll have to reschedule a meeting with Nasran to occur a bit to occur later so that I can cover this. Okay, so here's our generalized algebraic theory, and what Nasran is, or what Uche has done here. Nasran has done other great things. This is Uche's work. She's defined this generalized algebraic theory in GATLab, and GATLab is a core enabling technology for CATLab, the categorical computing platform from Topos Institute, and GATLab is they built and is now lies at the heart of CATLab. And the idea is that we can define a theory, and those I'm going to probably not do a very good job depicting this, but you're going to need to stretch your understanding a little bit for this. So I think everyone here is familiar with the idea of having with CATLab, can have define schemas, right? And we use @present to define a schema, right? And in that schema are different objects, for example, and HOMs between the objects, right? So we can have an object E and an object V, and we can have morphisms, HOMs, from E to V of source and another one of target. You remember that. And we have @present, right? And that's characterizing a specific presentation of a category. Category is freely presented by that. And we might have a different category for stock and flow diagrams and a different one, different schema, right? And we might have a different one for closed loop diagrams, right? @present. But those are all schemas. Those are all schemas. And they're of a certain theory associated with schemas. Lets you define a presentation of a category. There's a bit more to it, but the idea is that we have some theory behind this that we can present a category. Here, what Uche has done is at another level. We're defining our own theory. Okay, so it's almost as if like we're defining our own building blocks by which we can define our presentation of that. So like they're like the schema and related to category, there the building blocks are things like HOMs and objects, right? And then we have an @present, and we can say there's objects V and objects E, and the HOMs are source and target, right? That comes built into CATLab, that theory that we're using every time we do @present. We're going to see @present later, but we're going to be presenting this theory, not the schema theory. And this is defining the building blocks we're going to be using. Instead of having HOMs and objects, we're going to have our own building blocks. What will those building blocks be, pray tell? Those building blocks will be dimensions. It's getting really interesting. Units, but not any old units. Units for that dimension. Now, if someone's watching this from programming language background, they've realized, wait a minute, this is like a dependent type. The units, it's not just we're specifying any old units. any old dimensions, any old units. No, no, no. These are the dimension. These are the units for this dimension. Remember this notion that units are fibered over dimensions. So for a given dimension, think of the fiber in a bundle over it, right? Those are all associated with those dimensions. Another dimension will have a different fiber over it if the units for that, right? The units for length are very different than the units for time, for example, possible unit systems, right? Here, the units are specific to a dimension. And so when we give our presentation of this theory, we're going to be specifying our dimensions, and then for the dimensions, for each dimension, we could have different units. So like be a dimension for time, we can have units for that. Dimension for length, we can have units for that. Dimension for how we specify people. We might have, this may sound weird, but per person, like counting individual people. Another common one in epidemiology is per 100,000. So one might mean 100,000, 100,000. There. Okay, so those are some building blocks. What other building blocks are there? Well, we're going to have different ways of sort of manipulating these and so on. So we're going to have, for example, a dimensionless dimension, a time dimension. We're going to be working with simulation models, so it's going to be a time dimension. You got to define what the time dimension is for your presentation of this. And we can do things with these, right? Like we're defining a theory here. We're defining a little algebraic theory. So we have two dimensions. We can multiply them to get another dimension. We have one dimension, we could take its inverse to get another dimension. It's kind of interesting, right? And similarly, units for a given dimension. If you have units of dimension one, and you have other units of a different dimension two in general, then you multiply them. You get units of the multiplication, some unit of the multiplication of those dimensions. Now you'll notice that this little thing, which John Baez told me is called a sequent, I think. It's also called the turnstile signal, the turnstile symbol. What's to the right of it? This is very common notation. Well, it's a variant of notation common in type theory, which is really interesting stuff. So it's saying you have this context where we have dimension one and dimension two defined. If we have a dimension one and dimension two, and then we have units of dimension one and units of something whose type is a unit of dimension one, and another thing, unit two, whose type is dimension this, we can multiply them and get something of this, units of this, right? I should have explained that earlier. Similarly, if we have a dimension and we have a unit of that dimension, something who's drawn from the units of that dimension, so we have a unit of that dimension, we can take its inverse and we get something which is guaranteed to be a unit of the inverse of the dimension, right? So if we have something of per, let's say, a day is a unit of dimension time, and we do units inv, we'll get back a unit of dimension 1/time per unit time. So it'd be per day, will be the unit, right? And then there's a unit dimension of the unit dimension of the dimensionless. Okay. Now, this is just like awesome, Uchat. This is like, awesome. Okay, and you can see how beautifully she's documented this. Okay, but here's something that's interesting from a software engineering perspective. UJ factor out to reduce the brutality, and indeed that's the word for it, of needing to define all sorts of operations with stocks, flows, because we're going to be applying this. She defined a variable, and this is going to be a quantity. It's going to carry a dimension and a unit, but it's not any old unit, right? It's the unit fibered over that dimension, and this is related to, if you're wondering, pullbacks, etc. Um, it's fibered over this. So it's some unit compatible with that dimension. It's a unit of that dimension, right? So we have a dimension, then we have a unit. This is again where sort of dependent types come in. This is dependent on this type, right? So we have a dimension, we have a unit of that dimension. Then we can, if we have that, we could have a variable of that dimension and unit, right? Yeah, this is like incredibly cool, Jeff. I agree with your assessment. Okay, so this bar is going to give us legs, okay? Because we're going to be able to do, you may say like, what? Why a var? Well, look, it allows us to define what it means to add variables and like subtract things and multiply things and div. Now watch this. This is like uber cool. This is Uje's like triumph. A triumph. Give me a second here. So I'm going to take my hat off to Ujia for doing this. It's just awesome. It's awesome. Okay, so watch this. Let's consider plus. Think about plus. Okay, look, if we have something of a given dimension, a dimension, right? And we have a unit of that dimension, then if we have x, which is a variable of that unit dimension, and y, that's a variable of that same, mark my words, unit dimension. It's a unit for that dimension, right? We could take their plus and we'll get another variable for that dimension in that unit. We add these together. They're compatible dimensions and units. So we can add them together and get something of that same, right? The sum of them will be of that same dimension and unit. Notice that these have to be the same dimensions and units. Same thing with minus, right? But take a look at multiplication. Take a look at multiplication. Here we have, notice the context here, right? We have dim1 and dim2. You probably know where this is going. And we have unit 1 of dim1, unit 2 of dim2. So maybe like dim1 is length, or say it's person. Dim2 is time. And we have a unit of person, say count people. And we have a unit of time, say years. Then we can multiply these things, right? We can, if we have a variable of dim1 and unit 1, so some count of people, and we have another variable y of dimension time and unit years, right? We can multiply them and get something that's a variable of, well, it's the product of the dimensions, right? It's a person time, and its units are person years. And again, I mean, that's a familiar thing within epidemiology and modeling. Have some number of person years the population is living. It's a very useful quantity, actually, to capture if people's lives are being cut short by some disease, etc. You integrate it without for the base case, and you integrate it with the intervention. You see if you've allowed more person years in the population, right? And similarly for div. The important thing to realize, or a key thing to realize here, is that this allows us to combine things of different dimensions, right? And units for compatible with that, and get something of a different unit dimension. Whereas this has to be, when you add things, they have to be the same unit in the same dimension. Now, down the road, I think there'll be a combination so we can add things of different units for the same dimension, right? So we can add 3 days to 1 week and get 10 days. But that's coming. UJ has already done amazing work with this. But I think you could see where this is going. This can be relaxed a little bit so we could get something that's, as long as they have common dimension, then we can convert the units so they're common units. Okay, so we're doing this with variables, but a lot of the goal for that is that UJ didn't want to have to write plus and minus and div and mul for every combination of like stocks and flows and parameters and auxiliary variables. Like, that would have been brutal. Brutal, indeed. So now that we've defined this for variables, now we can kind of promote any stock to a variable, and we can combine it with other quantities that are promoted to variables. But there's logic here too. I mean, it's just awesome. Like, you just done an amazing job. Look at this. Check this out. Check it out. Okay, so we have a stock of a certain dim in unit. Okay, so we have a dim, we have a unit, and that allows us to have that tells us if we have a stock of that dim in unit, well, we have a type. Okay, great. Okay, now check this out. Any stock var can be created of type var anytime that we have a stock of a given dim unit, then we can get a variable of that dim unit. The fact that we can convert this will allow us to combine it with other things. So you can treat it like a variable, and we don't have to define this for stocks separately. And better yet, we don't have to define it for every combination of stocks, say, and flows. Okay, but check this out for flows. This is like virtuosity. Virtuosity, right? Okay, this is a San Diego Zoo hat. If we have a flow, and it comes from an upstream stock to a downstream stock, those stocks have to have comparable dimensions and units here. So the upstream stock and the downstream stock have to be of commensurate units, for the same dimension by extension, because dimension units are fiber different dimensions, right? And this is a time unit here. It's a time, it's a unit of dimension time. Okay. So if you have a given dim unit, then if we have a flow that goes between those stocks of compatible dimensions and units, with this being the time, then now we have a type that we can manipulate. And then we can have flows from clouds and flows to clouds, etc. But the point I want to highlight is, like, it knows about dimensional homogeneity. Like, it knows a flow has to go between stocks of this. If it goes between stocks, it has to go between stocks of comparable dimensions and units, right? Which is really quite sweet. Okay, so this is our theory. Okay, so it's as if EGS described. Again, take your mind up, right? You're used to describing, and Jeff is newer to it, but everyone else is quite used to describing at present for a schema category, right? And there were our building blocks are like HOMs and objects, these things, and attributes. That's what the schema gives us, that we don't have a normal category. So attributes, right? Now, what you just described as an alternative theory to schemas, right? So now these give us the building blocks, these things here. These give us the building blocks. So if we have a presentation on it, we can expect that we'll describe things in terms of these building blocks. So let's go see that. Well, we're going to do that. We're going to get there. We're going to get there in just a moment to present, and we're going to build it up out of these building blocks, these flows, these dimensions, these units. But first we have to define what's called a symbolic model. And this reflects the fact that GATLab allows us to compute with our theory, with this here theory defined by Ujia. It allows us to compute with symbolic quantities of this sort, or with actual encodings of them as in quantitative data types in Julia. So like a number for this parameter, a number for that stock at a given point. Or we can kind of deal with it as symbols, right? Like we might do when we have expressions, formulas in governing, the value of a flow of a auxiliary variable. Okay, so let's chat about this. So we're going to find a symbolic model. This is all GATLab stuff. Okay, so we're going to find a symbolic model, and the symbolic model is going to allow us to do things like multiply parameters without having any specific values for those parameters, but we'll be able to talk about like the value of the stock times divided by the value of the stock divided by mean recovery time, the I stock divided by mean recovery time. That is a formula, right? It's an expression. And it will have a unit associated with it. The stock will be of, say, unit persons, dimension person, and maybe the little parameter will be of dimension time, and it'll be mean recovery time, and the unit will be days. Well, if we divide the stock by that parameter, it will have a dimension persons per day. So that's a combination of symbols. And we can build up these expressions, these formulas of these symbols. This times that, plus that, divide by that, in a way that tracks the dimensions of all these different things, of the individual pieces, the parameters and the stocks and the flows, and of their combination, this times this plus this. And it's intelligent. It won't let you do something silly like add persons to persons per unit time. It'll say cannot do. That doesn't make sense. Those are incompatible. Right? But it will let you multiply persons times time, for example, but not add, right? So this is what we have to do. Now, here's the deal. Because we're building up these symbols, these expressions, we have to be conscious that we may have two expressions which we know sensibly have the same meaning, but which interpreted textually, like we look at the text, may not be the same, right? So stock I divided by mean recovery time parameter tau, so I divided by tau, is morally the same. It's essentially the same as I times 1 over tau. Right? But in terms of how it's written textually, the string, like writing it out, it's different, right? I divided by tau is not the same string as I times 1 over tau. But it's the same meaning, it's the same mathematically. And so Uche taking that into account. Similarly, if I write S times I, well, we all know because multiplication is commutative, that's the same as I times S. But the string is different. So in GATLab offers facilities to allow us to normalize, to recognize that, aha, those are actually the same. S times I is the same as I times S. Or I divided by tau is the same as tau times I, or sorry, 1 over tau times I, or the same as I times 1 over tau. Right? And so what Uche has done is put in place these normalization mechanisms, which allow us to normalize these expressions. So they have a canonical order to them, which means that we're not depending on the vagaries of whether it's x times y or y times x, whether you've written it down that way. You may have written down either way, but it gets normalized through to be in a certain order, and then we can compare dimension to dimension, unit to unit, for example, of these things. And so we're not thrown off by thinking person times time is different from something of dimension, person times time is different from something of dimension, time times person. It knows that they're the same because of this normalization. And Uche does this great work of you can see it sorts it so that we can canonically characterize it. And we can normalize for these things. Okay, so what would this look like? So look, if we have a model like this, stock and flow model like this for SIR, right? And then we have another one for wastewater treatment plant. Maybe we want to describe this in time units of days, and maybe want to describe this in time units of weeks. And we, just because it's convenient to specify the wastewater delay, maybe in weeks for a big city, copy shed per week. Maybe it's convenient to reason about this in weeks as our preferred yardstick for time, and here days, right? Okay, well, we can build that up. Now we get this at percent. This should be familiar. Remember, you've used it for at percent for schemas, which have HOMs and objects and attributes and that sort of thing. Here, because those are the building blocks for schemas, we present a schema. A schema for, say, graphs. Right? 2 objects, 2 HOMs, etc. Here, we're presenting something of this theory here, but more specifically, we're building up this symbolic model, this free-dimensional stock flow algebra. So it knows we're building up these formulas. So, well, what are our building blocks? Well, they're dimensions. That's a type here. You can bet there's going to be units of that dimension. See, that's a type too. It's a dependent type. This value depends on this type depends on this value, right? Which is of dimension dim. Think about that. That's not trivial, what I just said. This is a type, units of pop dim, but it's a type. Which type it is depends on this value itself of type dim. So this is going to carry some value, and this type is going to be dependent on the value. It's almost as if this is what we call it, a dependent type. It's almost as if, we have a length of an array. Sorry, we have an array of length n, where n is a value at runtime given to us. Maybe there's a function passes in n and it returns an array of length n. There, it's a dependent type. The type is dependent on that value. This type is dependent on that value. It's a unit for that dimension. for that dimension. Then we have to have time units, right? We need time units, yeah. We're going to need that for our, recall, for our flows, right? Our flows, we're going to have a certain time unit for those that we want to use. Here will be weeks, here will be days, right? Here's our stocks. This is a type. Again, Uche has defined this theory, so the building blocks are custom to our area. We have built a little language and type system. Uche has built it. And once again, I take my hat off to Uche. She's built up this little domain-specific language and associated type system, multi-level type system, right, with dependent types, right? And so it knows about stocks, it knows about as building blocks, it knows about flows as building blocks, etc. It knows about parameters, and there we go. There are stocks, there are flows. The flows, this is a flow. Remember whose type, right? Remember the stock goes from it's a flow, and its dimensions and its units will be dependent on the dimension and units associated with its upstream stock and its downstream stock, and it will enforce, the type system enforces that these are the same. The dimension of this has to be the same as the dimension of this. The unit of this has to be the same as the unit of that. And we're measuring this flow in days. Measuring this flow in days. So here are parameters. It just states what the dimensions and units are of those parameters, right? So she's specifying this. Remember, this is a symbolic model. She doesn't have to give values for these. She just says it's a quantity of dimension of unit days or whatever. And then here, this is wastewater surveillance associated with that. Okay. Now, and this has flows that are weeks, and one of them is a flow in from an external cloud here. And then you have parameters which carry certain units and actually these, you notice this is like dim times pop. So copies per person in the population per unit time. That is sweep. And you get a similar units associated with this. This is a shedding inflow, wastewater time constant. Okay, so she's built up as a presentation of this theory. She's built up a little presentation of it for the symbolic model. What can you do with that? Well, you could combine these things. You can combine them. So you can combine, for example, this is just sort of showing that testing it out and taking a look at it. Look, is the inverse of the wastewater delay, for example, the dimension of the inverse of the wastewater delay equal to the dimension of tau? Yeah, it is. You have, I guess yeah, here's tau here, here's wastewater delay, and this is of something whose dimension is 1/time. This is something of dimension time, the wastewater delay. So the dimension of the inverse of the wastewater delay, 1 over the wastewater delay, is going to be equal to the dimension of tau. You have the multiplication of the variables. She could imagine a multiplication of this parameter with this stock, for example. And she gets a var out, and she could ask for its dimension, for example. she can also compare, like if I have sigma times I, is that of the same unit? That is the unit for that equal to the same unit as the shedding in variable. This one, and this says it is. Notice that these are she's sort of consing up. She's having these formulas here, like multiplication of these variables, but she's able to take their dimension. She's able to take their units because they are unit and dimension bearing quantities. They are symbolic, but these expressions, these formulas, encode the dimensions and units, and it tracks them all through. But beautifully, it prevents us from doing something that's incorrect. Like if we try to add the value of S bar of susceptibles, right? And we try to add that to the value of a flow, it'll say no can do. There's a main error. In other words, they're in short, they're not of the same dimension. They're of incompatible dimensions. Hmm? Here's testing commutativity. S times I is the dimension of S times I is the same as the dimension of I times S. Hmm? And similarly for units here, which is sweet. And so here, you can build up these expressions by multiplying things, by dividing things, by adding things of appropriate dimension or appropriate unit, and building them up and building them up, and it computes through these symbolic expressions, not carrying any particular values, any value for the stock, for example, value for the flow, by carrying dimensions and units. It carries through there's dimensions and units as you come on. Think about that for a moment. So we have this theory that describes these things we really care about, dimensions and units, and that describes how they're related to stocks and flows. And it describes them, not just encoding them, but these operations on them and how we track things through these units. And we can, in GATLab, say we want a symbolic model of this sort. And we have to do some work to deal with the fact that S times I is not textually the same as I times S, but the dimensions. And dimensions, if you do it naively, will look different, but they're intrinsically the same in terms of their mathematics. But we can capture them. It's gorgeous. You just captured it. So that's one way you can use this. And it's very powerful, right? I mean, look, this is what we want, right? If you think about it, if we want to build up expressions in stock flow models, like for the value expressing the value of a flow or expressing the auxiliary variable, dynamic variable, build up expressions. We want to be able to track the dimensions of that. And we want to be able to call out if there's something crazy going on, like we're adding persons to person per unit time, right? For adding dollars to people or whatever. Adding length to length squared. And that's exactly what we can do here. We can build up these expressions, have the dimensions characterized, have the units characterized, have the dimensional homogeneity checked as we're doing it. It tracks it all through in this dimensional system. So this is pretty nifty, but that's not all. Let's see what else we can do. Let's see what else we can do. when we're simulating a model, we can do a lot more. We need to do more than characterizing formulas and the dimensions of those formulas. We want to have actual values for stocks, actual values for flows at any one time, actual values for parameters at any one time, often invariant. But those values are not solitudes. They're not in isolation, right? They have dimensional information, unit information associated with that. That per day value one, what one means depends on the unit of time, right? Per day, per unit time value of one, we need to know what the time unit is to know how to interpret that, how to interpret that value of one. If it's per century, it's a very different implication if it's per femtosecond, right, or per second. Dimensions and units capture structure. And when we're computing, like numerically integrating a model, simulating it, it behooves us to carry that structure on. Less so that we'll find errors, but more so because we want to be able to express things, perhaps, for example, to the user, have a graph that shows people per unit time getting sick, and maybe they want to convert it from per year to per day or per week, right? Maybe they want to convert from miles to kilometers for the mileage efficiency, right? Or what have you. For distances. So GATLAB lets us do this through these things called instances. And here we're going to be characterizing a quantity that's encoded with Julia types, actual Julia types. Okay, it's not going to be symbolic; it's going to be actual encoding at Julia types. And so, we're going to define specific encodings for, like, the dimensional vector, particular values associated with quantities, and in particular units relative to some kind of based on a reference unit for a given dimension. So for a given dimension, say for the time dimension, we'll have a reference unit. So like days, we'll have a ratio of 1 for that reference unit. Weeks, we'll have a ratio of 7 because 7 days make up one week. So the unit week will have a ratio with respect to the reference unit days, 7 times as long. Right? But here we're actually specifying encodings of these things. And so when we have a dimensional product of powers, for example, when we multiply things, if we multiply people times time, we're going to have to add these powers 1.0, 1.0, 0 by adding up these vectors. Before we didn't do it, it was tracking dimensions as combinations like expressions of formulas times and person, dimension for person times dimension for time. Here we're actually encoding them as numeric values. And you notice there's this characterization of what's like the of the this is dimension one vector for sort of the dimensionless vector, for example, or the time vector. This is how it's encoded. So, and you notice here's the rule with the ratio to the reference units, multiplying when I multiply things of different units. So here we're not computing with symbols, we're computing with actual values. We're going to be computing with values for parameters, values for stocks at a given time, values flows at a given time. But those are going to have encodings of their dimension and their units associated with them. And units are going to have this knowledge of what their length of their yardstick is relative to the reference thing. The week is no, I'm 7 times as long as the reference one. And that will allow us, if needed, to like convert between things down the road. Yeah, so this is pretty nifty, and there's some, there's some bookkeeping that's needed for that Ujia has put into place here, which is really quite pleasant. Okay, so she's also got some nice abstractions to build up a little model. Okay, so here's her sort of testing it out, and there's a functor in CATLAB that's used to kind of map, as you might expect. We're basically mapping the model structure that we have for our model here, SIRE, etc. We're mapping that over and giving things values, like the initial value of S is 1,000, initial value of I is 1,000. The value of parameter beta is 0.3, but not just 0.3, right? It's 0.3 per day. I mean, that's the units. This is 0.1 per day, right? This is 1,000 people. So she has this nice little language where we can define these dimensional quantities. They carry value, yes, but they carry units, and the units are fibered over dimensions. So the unit will tell us about its dimension. The dimension knows I'm a unit, or sorry, given unit knows I'm a unit of this dimension. That's my base, right? I project down to there in the base space. Right? I'm in the fiber over time. I'm in the fiber over time length divided by time, people divided by time. We keep that information. This is pretty nifty. Okay, I'd said like within the same model, you can have different areas of it with different time units for convenience. But when we integrate it, when EGA integrates it, it's with respect to a sort of common time dimension, so she can integrate it up. But it's convenient to be able to express time constants with respect to, a convenient time dimension. Okay, so check this out. This is like virtuosity. Check it out. Look at this. Okay, so basically she sets this up as an ODE, an ordinary differential equation, right? Sets this things up. And she knows how to evaluate all the expressions of the flows from how they're defined in the model and from the values on which they depend. And notice she has to convert the wastewater flows. Remember, those were measured in weeks. These things here. She converts them to appropriate day-based values, right? Convert units here, and that uses that ratio information. And here she's Um, she says coordinate-free ODEs. Uh, but you have these values here, which can be computed, and she can then use that for numerically integrating it to sort of set this up. So she has an ODE problem, and she can simulate it, and she can get out results that are dimensional quantities, that are not merely numbers, but are numbers with associated units and by extension dimensions. This is really impressive. This is really impressive. Okay, time is running on. A few things that I see as priorities for the coming work. I'd really like to see this integrated with stockflow.jl. And I think we're going to need to figure out how it gets integrated. I have many ideas of how we can use it once it's integrated. But my naive thought, and I think some of this came from Mehdi's comments, I think, too, but I've talked with Uchi about it. And she had noted it. I think we might be able to, in a stock and flow schema, have attributes, and attributes can be GATLAB expressions. And I think we might be able to encode dimensional and unit information using these sort of building blocks that these sort of structures that Uche has manipulated, for example, in the symbolic models, the sort of associated with these expressions here in terms of dimension, etc. But they might be normalized so that we can compare and test whether two things are equal in a more reliable way. I don't know if this will work. I think it needs to be thought through by a collection of people, and hopefully today will provide a first step towards getting people up to speed on this, so we could really start to think through, like, does this work? Like, could we each stock, so just like in an ABM schema, we might have an object for people, it gets mapped over via a functor, appreciate over to a set, and each person can have an attribute value for their age. Right? It can be a real number, for example, age. So we associate object, and there's a morphism, an attrib mapped for the attribute down to an attribute age. And that means each person is associated with an age, can be mapped down to an age. I think we might be able to do something here, like each stock can be mapped to an attribute, which is a GATLAB expression of unit and dimension information, something like that. I don't know if it works, but I'd like to get discussions going about it, and then maybe we can refine that. I'm sure it's broken at some level. It's something that needs refinement, but at least we can get discussion on it. I think this is incredibly great stuff, and I think we need it in StockFlow. Now, once we have it in StockFlow, I think there's all sorts of ways we can do it, right? We can integrate into the validation, test formulas for dimensional consistency and unit consistency, potentially convert units as needed, much as UGA has done here to convert things, but be able to allow intelligence along that, maybe formula editing support and something like Model Colab and derivative tools. potentially reducing parameters, but that's further on. Um, and then I'd really like to work with a friendly category theorist on categorical basis for that. I kind of spoke earlier about this and waved my hands. I mean, the fact is, this is a good idea. This abstraction, and Evan had pointed out its applicability, but it does not cover units. Like there's a whole nother level for units and reasoning about units. This covers dimensions. It's an elegant model, dim graded monoids. It goes a certain distance for dimensions. There's some other gaps with it too, like it doesn't address dividing dimensions or dimensional quantities, but we really need units to be fibered over dimensions, and that's not accounted here. And I'd like to put that into place within coming months by working with someone on the category theory side to get an elegant theory. Okay, so what are some remarks here? Well, look, dimensions provide really powerful support for modeling, if we're doing systems modeling, right? And at a deep level, the Buckingham pi theorem teaches us, or forces us to reflect, that if we're not characterizing dimensions in units, we're leaving out key understanding of the structure of the world. We need that information to do justice to our model, to have meaningful captures relevant structures in the world. It's hugely relevant. Capturing units within a given dimension offers further advantages, including, conversion of values, etc. GATLab provides this amazing support for building up these little domain-specific languages with their own dependent type system, such as UGA has in a tour de force built. And the sort of dimensional and unit information we've seen, it can be characterized for symbolic expressions, I think of great relevance for describing stock and flow models and checking dimensional consistency. And for numeric encoding, such as we've seen for integrating up, right, a model. For symbolic models, Uche has shown how you can perform normalization, unitality, associativity. Evan provided guidance, but Uche took it off and ran with it and did an amazing job. And it's just amazing. And I think integration of this GAT into stockflow.jl will really provide amazing benefits for the users. And I'd really like to see if we can work with others to get a salient theory of what's going on here so that we can describe it hopefully at ACT, Applied Category Theory Conference this summer in Tallinn, Estonia, in July, early July. Okay, that's all I want to